Okay, so we are in this book here, Causal Inference and Statistics, a primer, and we're on question 1.5.2. Here's the question. It's a little bit wordy, and so I suggest that you probably read this rather than me reading it, and also write and take notes on what is being said, because there's a lot of information conveyed there that can make it a little bit tricky. But I will try to give an overview of it. So the idea is that we have a data set that contains the following information. We have the variable z, which is whether or not the person has a particular syndrome. Okay? X, and x is the probability that somebody is, well, it's not the probability, it is whether or not somebody is taking a treatment or not. And then y is the outcome, where they either die or don't die. Okay? And so the idea here is that, well, there's a couple of ideas. So one is that the probability of somebody having the particular syndrome is given by the letter R. Okay, so if they have the syndrome, it's R. That's the probability of them having the syndrome is R. If of them not having it is 1 minus R. Okay, and well, that syndrome is of course going to affect their outcome, right? Whether they die or not. And so the outcome are given letters of P, P1, P2, P3, P4, and those all correspond to whether they live or die and whether or not they have the syndrome. So P, again, if you read it up here, is a conditional probability of living or dying. Again, you should probably take notes on all of those because it's, you'll get mixed up. And then there's also X, and X is the probability of treatment, of receiving a particular treatment. And of course, treatment is going to affect outcome, and apparently whether or not somebody has the syndrome is going to affect whether or not they're taking the treatment. I think that the story that's given in the question is the syndrome makes it uncomfortable for them to take the treatment. Okay, so that's the background, and then there's 3 parts here, and so we'll go about trying to answer these. Okay, so the first one is based on the model, the model that we just looked at. We're supposed to compute joint distributions, joint probability distributions, all 3 variables, then every combination of the 2 variables. Okay, so let's kind of go about doing all of this. So this gets a little bit messy, but so what we're looking for is probability of x, y, z, and so it's going to be, well, we're going to go through every combination of x, y, and z here. Okay, so in order to do this, we can, or one way that we can do this is to decompose our joint probability distribution, right? And what we could do is to say the probability of z, so the joint distribution could be the probability of z times the probability of x and z times the probability of y given x and z. Okay, and so notice how this maps on really to our DAG, right? We have the probability of z. So, well, okay. So first, let me say that we could change the terms that we were using here, right? We could say the probability of y times the probability of x given y, and da 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 da. We could choose different individual terms, but we have chosen this set of terms because it maps on to our DAG here, right? So notice that the probability of z has no, according to the DAG, has no incoming variables. It's independent. Well, that's a weird thing to say. I don't want to use independent. That word gets overloaded. But it's not being affected by anything else, at least according to the DAG. And so we just have P of z. X, however, is, according to the DAG, being affected by z. So the value of x is conditional on z. And so we use the conditional probability of x on z. And then finally we have y. And y, again, is conditional on 2 things, x and z, right? And so we have the conditional probability of y given x and z. Okay, so now we need to go about finding the different probabilities for z equals 1 and z equals 0. Okay, and then for x, right? And so we want x equals 1 given both conditions of z, and x equals 0 given both conditions of z. Okay, and then y. Okay. So we want y given all combinations of the values of x and z. Okay, And so you can go through this and kind of see how I've solved this, or it's hard to say that I solved it, but this is going to act as a menu. This whole thing is going to act as a menu for the following questions. Okay, so again, where I am getting a lot of, where I'm getting many of these things is just simply coming from the information that was provided in the question. And again, there's a lot of information in the question, and so you probably need to take notes and understand what P1 is supposed to mean, P2, P3, P4, Q1, etc. Okay. Okay. So that's the joint distribution of all three variables, and then we want these two-way variables. Okay, so we'll just look at x, y, and then I'll let you and you can just look at my answers on the Colab sheet for the other ones. But hopefully x, y will kind of help you get along your own way towards solving it. Okay. Okay. Oh, I skipped a part. Apparently, I forgot. I'm sorry. So what we've done up here with the three-way joint distribution is we just decomposed everything into the individual terms and found the values for these terms. Okay. But if I actually want the joint distribution, I have to go back through and recombine them, right? So for all of them, for x naught, y naught, z naught, well then I need to find the probability of z naught, right, which is up here, z equals 0. That's 1 minus r, so 1 minus r is in there. And then I want the probability of x naught given z naught, okay, x naught given z naught, and we find that that's 1 minus q1, so 1 minus q1 goes there. And then we have the probability of y naught given x naught z naught, and that's 1 minus p1. Okay. Well, so we can go over here to this part of the menu, and I'm looking for everything being 0. There it is, 1 minus p1, and that's what I got. Okay. And so that becomes the joint probability distribution, or the joint probability, I should say, for x naught, y naught, z naught, and I can do that for every combination of x, y, and z. Okay. So that's how I go about that. Okay, now we'll get back to the two-way joint distribution. So now for these two-way joint distributions, the way that we do this is we need to marginalize out the omitted variable. So if we're going to look at x and y, the probability of x and y, okay, what I don't do, I repeat, is just look at the probabilities of x and the probabilities of y's and multiply them, okay? Instead, what I do is I take my joint probability distribution and I marginalize over all values for the omitted variable. So for x and y, I sum over every value, possible value of z, right? Because I'm trying to get rid of z, so I need to account for all values of z, okay? So for probability x naught, y naught, well now I need to look at two joint distributions here. Okay, I need the two joint distributions where I have x naught and y naught, and then I need both values of z, z naught and z1. Okay, well these values, right? These values we've already found those, so it would be this value, right, which is what we have here, plus this value here, okay, and that's what we have here. And similarly, let's just go down to the bottom. Well, let's go to this third one here. If I want the joint probability of x1 y naught, then I need every joint probability where I have x1 y naught. So it looks like we have a x1 y naught here and here, and then I need both values of z, z naught, z1. And so my answer should be this plus this, okay, and that's what I have there. Okay, and so you can go through the rest and find every joint probability. Okay, all right, good. Okay, so now we're going to calculate the difference between this term and this term. So what are these terms? It's the probability of dying given the receipt of treatment minus the probability of dying without taking the treatment. Okay, and we're doing it for three populations: those with the syndrome, those without the syndrome, and then the population as a whole. Okay, so what is this? What is this difference? This difference is the probability of how do I want to say it? this is the effect of taking the treatment on dying, right? So the difference in dying, or the difference in the probability of dying between taking the treatment and not taking the treatment, if we believe our DAG, is the causal effect of the treatment on preventing death or causing death, however it may be. Okay. Okay. So for the first population, or for the first population that we're supposed to calculate this with, it's those carrying the syndrome, right? So that means that is Z1. Okay. And if you go back up to the question and you read these, you see that this probability is given by P4, this probability is given by P3, and so that is just this right here. Now for those not carrying the syndrome, in other words, Z equals 0, you'll find that this probability corresponds to what they're calling P2, and this probability corresponds to what they call P1. Okay, so that's all pretty basic. And then we come to the third one, which is the population as a whole. Okay, so we're no longer discriminating between those with and without the syndrome. Okay, so this gets a little bit tricky, because I think one of the first things that will come to mind is to just try to somehow cram in the joint probability distributions that we found earlier, maybe this XY1. Okay, now that is part of the process, but it's not exactly what we need, and let me show you why. What we found up here were the marginal probabilities where we have marginalized, or I'm sorry, the joint probabilities where we have marginalized out one of the variables. But what we are being asked about are the conditional probabilities. Okay, now joint probabilities and conditional probabilities are related, but we have to do some work. And the way that we can go about doing some of that work is to first use Bayes' theorem. Okay. Or it's not really even Bayes' theorem, it's really just the definition of conditional probability. Okay, so the definition of conditional probability is this right here. It's the joint probability divided by the thing that is being conditioned on. Okay, so we do that. So that's the conditional probability here and here. And the reason that we do this is because now we actually have joint probabilities. Right? So there's that. Okay. So this joint probability distribution, well, we're going to track it here. It doesn't change here, but it's the numerator of this first term. Okay. So it all gets very big. This is the final answer right here. But this is the joint probability of x1, y1. And this is the joint probability of x0, y1, okay? And then for the denominators here, x1 and x0, well, this is the joint probability distributions where we sum over, we have to marginalize over y, right? So we actually already have xy. And so I need to, just as we marginalized over z to get rid of z, I'm going to further marginalize over y to get just x by itself, okay? And so here we have x1 over both conditions of y, and then we have x0 over both conditions of y, okay? And we already have all of these in what we found above, and so we take what we found above and they get put in here. Okay, so it's a big long answer, but that's how you go about constructing it. All right. Finally, use your results for B to find a combination of parameters that exhibit Simpson's reversal. I'm just going to punt here because it really just becomes a mechanical thing, but I thought maybe I would just remind you of what this means, of what Simpson's reversal means. So it just simply means that we find a situation where if we include or exclude a given variable, this reverses the sign of the estimate. So for example, if we had that Py1 x1 z1 minus P1 x0 z1, so in other words, the probability of dying, given that you have the syndrome with and without the treatment, okay, so the effect of the effect of treatment on dying when you have the syndrome, if that was greater than 0, okay, but then we either marginalized out Z, so now we don't care about whether or not you have the syndrome, and then that estimate becomes less than 0. This would be a reversal, and so that would be an instance of Simpson's reversal.